Thank you. So I wasn't quite sure exactly what to do since it's a varied audience. So what I will do is try to introduce scattering in the context of gravity, and then talk about some of the developments that have been made in the context of gauge theory, and then just widely discuss broadly how they may or may not generalize in gravity. So the usual approach we have to amplitudes is that we start with extract some Feynman rules after possibly gauge fixing as needed, and then we calculate the amplitude as the sum of those Feynman diagrams. And of course the object of things we can measure, the cross-section, differential cross-sections related to that amplitude squared. So there's no reason why we can't do that in gravity. And so in that case we start, and I'll think of just here pure gravity. I'll take an Einstein-Hilbert action, and let's put in couplings for good measure. So here's a kappa. And then I want to expand this around flat space. So all I'll talk about is amplitudes in flat space. And so I'll expand around flat space, and my fluctuating field H will be my graviton field. And doing so, what I end up with is a lot. Now let me write it schematically. There will necessarily always, all the terms I will have will necessarily have two derivatives. That comes from the fact that I have the curvature term that has two derivatives. There's a quadratic term, there are cubic terms, and if I, well, let's put in our kappas. Plus da da da. So here we have infinitely many terms, so that's the first thing to notice. So there are infinitely many terms. They're all two derivative. The first one, I mean, in any case, I'm suppressing indices completely here. But if you really love indices, this is heaven for you.
Otherwise, it's hell.
That's right. So you get this delightful mess of indices. The first term is not so bad. It's really just what is going to give us our propagator. And in order to extract anything from this, we of course need to gauge fix. And a typical choice is harmonic gauge or the Donda gauge. And I'll tell you what it looks like with indices, just for good measure. Here. It's like that. So once you do that, you can extract a propagator. It has three terms, but it otherwise, and lots of indices. Otherwise, it's not too bad. It takes up a line in this paper I brought with me here. Then you can extract the rules for the cubic vertex. So that, of course, gives us some cubic vertex. This gives us some quartic vertex. The higher point gives us endpoint vertices. And the expression for the cubic vertex is this thing here. I'll can send your paper around. And it doesn't look so bad. It's only 4 lines, but each of those terms in there, and there are 3 terms in each line, is a separate line, so it expands out a little bit. The thing at the bottom here is the 4-point vertex. And I didn't pick this paper completely arbitrarily. This is a paper that calculates the 2-to-2 scattering amplitude for gravitons. And for this, we have to simply add 4 different diagrams. And they look like the usual ST and U channel as well as the contact term, 4-point contact term. But it's not completely arbitrarily chosen because this weekend we celebrated Gary's birthday. And this was Gary's first student. And there's even, after doing all this, so this was the 4-point term. This is the value of the T channel. And it continues on the other page over here. And even at the end of this, he actually thanks Gary for suggesting this problem. Okay, so poor Shannon. first student went through all this and calculated it and found that after each of these terrible diagrams, it simplifies dramatically. And so let me tell you what the answer actually is. If I'm in D equals 4 dimensions, I can write it very compactly. So this is the tree-level 4-point amplitude in gravitons. Here, let me call the states 1, 2, 3, and 4, label the momenta. The gravitons are spin 2. They can have helicity plus or minus 1. Let's take the first two to have helicity minus. The other two to have helicity plus. And then I can write this very compactly as follows. And I'll say a little bit more about what everything is. So very compactly like this. So S, T, and U are the usual Mandelstam variables. Then these angle and square brackets that appear here, those are spinor helicity formalism that encode the momenta and the polarizations of the gravitons in this case. I'm not going to go through the spinor helicity formalism. If people are interested, I'm happy to talk about it some other time. But this is simply a way of encoding the momenta. I can also write this in general D. And in that case, of course, I don't have helicities to specify. This is still tree level. In that case, I can write it as the Mandelstam variable S times a color-ordered gluon amplitude and another one, but with different ordering in the lines. So what are these ones? These are 4 gluon amplitudes. They're color-ordered, meaning that I picked off the color trace. That means that the ordering of the particles matter. I multiply 2 of those together, and I multiply by a Mandelstam variable, and that's the answer, no matter what structure I otherwise have. And this is also true for the 4-dimensional case that it simplifies like this. So if you want to think out what these ones is, and you're more used to thinking about disk amplitudes, think of this one as 1, 2, 3, 4. And this one is 1, 2, 4, 3 with your vertex operators insertions. And it's not a coincidence that I write it like this, because if you're calculating these as open string amplitudes, you just have to change the function of the variable S here in front slightly, and then you get the closed string amplitude from that. So the closed string amplitude factorizes into a product of 2. And this was noticed first in 86 by Cavai, Levellin, and Tai, so these are known as the KLT relations. It generalizes to higher point also at tree level, although you get a bigger sum of products of gauge theory amplitudes, of open string amplitudes. Okay, so the bottom line is that the answer for this amplitude is extremely simple, much simpler than anything that we went through with Feynman diagrams would indicate. So there should be some better way of calculating. So let's first think about why were there infinitely many terms in this expansion here. So one thing that appears is, of course, the determinant of the metric. The metric itself has a finite expansion. The determinant of the metric is going to be a finite expansion. But the square root of the determinant would generate infinitely many terms. The other place you get infinitely many terms from is from inside Ricci, because that depends on the inverse metric. So that also generates infinitely many terms. So that's why there are infinitely many. So maybe we could avoid this if we treated the metric and its inverse a little bit more on the same footing. And so there is an alternative way to expand. And that is to say, let me think about my G mu nu as an exponentiation of my graviton field. And so I now regard this as my matrix, where you take the matrix in the usual way defined by a series expansion. Now the inverse metric is on a completely equal footing to that. So we have that. And of course the determinant just gives us e to the trace of the graviton field.
If you doesn't have a canonical determinant?
It doesn't have a canonical, oh, what, sorry? It doesn't have a canonical?
I mean, it's like, right, that's the price you pay for this? Or?
So it's good. So what I pray for this is at the end of the day, it's going to be how I gauge fix and what my ward identities are going to look like. So there is a price to pay. At the end of the day, it makes life a little bit easier. And this calculation that Sanon did can be done in just a couple of pages if you like. But it still doesn't solve the problem for higher point. At the end of the day, I still have to deal with my field, so my field age. So it just helps a little bit in intermediate bookkeeping stages. Okay, so there are better ways to calculate. And so one thing I will do here is to outline some of those better ways to calculate. One of those better ways to calculate is recursion relations. So that will be our next subject. Now, I realize that many of you have heard about recursion relations before and seen the details. There are probably also some students who haven't, so I'll try to schematically explain what it is, but I will not prove any formulas with it at this time. So the idea is the following. We have amplitudes, let's call them AN for n-particle amplitudes. They depend on some data. The data that we give them is the set of momenta for each of the particles, and then something that specifies what the type of each particle is. So if these are massless particles, which is what I'll focus on, because we like gravitons, gluons, so on, then the types will be, for example, I can specify their helicity. And let's also, again, reiterate that I want these to be external momenta that are on shell. I'll focus on the massless case. And then I also want these momenta to satisfy momentum conservation. So those are the two properties that this input data has to satisfy. Now an amplitude is an object that has certain poles, it has certain structures, and one thing that you can exploit is those analytic structures in order to actually calculate the amplitude. There's a very efficient way of doing that by just working with a single complex parameter. And so we introduce a complex parameter by shifting the momenta. And I will shift them in a quite generic way. Namely, I'll introduce p hats that are my original p's shifted by this complex parameter c times some other vector q. And I want this q to be null. So q is null. And I want also that its dot product with the p it shifts, the original p, should be 0. That way, I ensure that my shifted momenta satisfy the on-shell condition. So I also want these guys to satisfy my momentum conservation condition. So I simply assume that my qi add to 0. And this gives me that my shifted momenta add to 0. So now I have introduced a complex parameter z. And my amplitude I can now regard as depending on these shifted momenta because these ones satisfy the same constraints as the original ones. And so now I have an object that depends on c, which is my shifted amplitude.
Henriette?
Yes?
Is Q supposed to be real?
No.
It's not?
No, it doesn't have to be real. In general, if you insist on everything being real, then you'll have a problem satisfying all these conditions, of course, at the same time. So we're happy in the process of complexifying the amplitude. We take it into the complex plane. In fact, I'm happy to regard the unshifted momenta also as complex variables. Yeah. Good. So let's look at this thing here. Let me assume that I'm only focusing at the tree level. Then this function that I have here of c can now only have simple poles. Why is this? Well, the original tree amplitudes can only have poles where I have propagators. Propagators appear where some sums, they're 0. They give me poles where some sums of momenta are add up to be null. And when does that happen? Well, generically, we'll assume that doesn't happen. But for the shifted momenta, then let me be a little more specific. I have some capital P here. It's a sum, say, of P1, P2 hat, etc. Some subset of the momenta. I'll square these. Now, I can't have anything in here that depends quadratically on Z because of my condition that all the Q's are null. And so this is going to be something that is linear in C. So linear in C, let me say this. This is linear in C.
Wouldn't the sum of some Q's be non-zero? I mean, the square of the sum of the Q's is not actually zero.
The sum of this, good. Yes, I need another condition. I also need, thank you, that Qi dot Qj is 0. I want that too. Yes, thank you. So I want this to ensure that this one is linear in C, so that my function an of z has only simple poles.
And these constraints can always be satisfied for an arbitrary choice of...
So there are explicit ways of satisfying these conditions. So So for generic input momenta, the unshifted ones, I can find explicit representation where, for example, I shift just 2 lines. That gives me one example. I can allow to shift all lines. You can always solve these constraints. And you can do them in various different ways. I'm just being very generic here. Now, anyway, this object has only simple poles. So they're located in different places. And as I mentioned, I'm assuming that my momenta are generic. And that also ensures that none of these poles will lie on top of each other and give me a double pole. Then I want to look at the object, which is the shifted amplitude divided by z. In addition to all the other poles, it has a simple pole at the origin. And now I take a contour integral and I surround all the poles, taking this contour. And then I will get 0, provided that my amplitude doesn't have a pole at infinity. And a sufficient condition for ensuring that is that my amplitude goes to 0 as I take this parameter z to infinity. Okay. So that also means that the sum of all the residues must be 0. And in particular, that means that the residue at z equal to 0 must be equal to the sum of all the other residues. So all the poles away from that. But when I set z to 0, I simply recover my original unshifted amplitude, which was the thing that I wanted to compute in the first place. Now, for each of these residues, what happens is that when I evaluate them, there's a pole that is going on shell. So if I draw a diagram, here is a particular pole that is responsible for a momentum. When that goes on shell, the amplitude factorizes into 2 different parts. Now evaluated, I indicate with hats around on the legs into two different shifted amplitudes. And I then simply have to sum over all of those. And in equation language, what I'm saying here is that my original amplitude has now become a sum of a product of lower order amplitudes. And it turns out there is a suitable momentum also, like this. So I'm being very schematic and a little brief here. The point is that each of the residues, the amplitude factorizes into 2 other on-shell amplitudes. You evaluate them at the value of c that ensures that the momentum that runs between is null. That's where the pole is located. Then you have, and that is actually thanks to this extra 1 over c factor, you generate a simple factor, which is just the unshifted momentum. So a scalar propagator for the unshifted momentum that runs on this channel here, times a left and a right amplitude. And when you count the lines, then you'll see that each one of these ones have lower number of legs than the original one I started with. So the bottom line is that what you get here is a recursion relation that allow you to calculate a 3-level endpoint amplitude from the lower point amplitudes of that theory.
So Henriette, what was the fundamental reason why all these poles at z non-zero factorize, but the one at z equals 0 doesn't?
The one at z equal to 0 is very special because I engineered it to be like that.
I see.
I picked to actually multiply by 1 over z in order to get there. And I don't already have a pole that's equal to 0 because I'm assuming that my external moments are generic, so no subset of them add to 0. Yeah.
Why does this all only at tree level? It seems
good. So at tree level, I only had simple poles. At loop level, an integrated loop amplitude has a much more complicated structure. At tree level, amplitude is a rational function in the momenta, but loop level amplitudes have locks and so on, so they have branch cuts much worse. So
what happens when the subset ends up to 0? I mean, then it's...
So at non-generic points.
Yeah.
Good. At non-generic points, you have to recover some of the structures of the amplitude. Namely, actually, I will talk a little bit of that. There's soft and collinear limits and so on. We'll come to that a little bit. We'll also come back to talk about what happens at loop level and what you can do there. So we'll do that. Okay, now, this is very powerful. There are various implementations of it. The most famous one is called the BCFW Recursion Relations from Bern, Cachaso, Feng, and Witten. Brito. Shoot. Brito, of course. Delete from recording. Oops. Okay, I'll be banned from Europe. All right, so, good, yes, Brito, Cachaso, Feng, and Witten, of course. Good, so with these recursion relations, I can now go ahead and I can calculate graviton amplitudes. And the way that I can do so is as follows. In particular, for the 4-point graviton amplitude, it is very simple because I can calculate it from just one diagram. And so I get, in this language here, I basically get a single diagram. Let's write it like this. This is what we call M4. Can be calculated in this fashion, and in less than a page of doodling, then you actually get the answer very, very quickly. And even better, now that I have this one, I can then recycle that in to calculate the 5-point graviton amplitude, etc., etc. In fact, one can prove various different formulas for the n-point graviton amplitude. So this is powerful and fun and avoids all the problems with indices and many, many terms. But there was a reason why I wanted to start out writing this action, because what we've learned now is the following. What we learned is that the input I needed for calculating all the tree-level graviton scattering amplitudes was simply just the information that sat inside here in this vertex. And it's even a little better because, especially in 4 dimensions, there is a structure called the little group scaling that you can use when you use these spin helicity variables. And that completely fixes the form of that 3-particle interaction. And then you can recycle that in and generate everything else from this. So that means that all of this other stuff is completely redundant and useless.
How did you do that?
The what?
I mean, let me ask the question this way. In gravity, I understand that there is, in a sense, no new information in those higher order terms. But if this was a scalar field theory, there would have been...
Good. So I'm going to come to exactly that. When can you do this?
Yeah.
Good. We'll come back to that in a second. So in this case here, this is fine. And it actually has a complete parallel in Yang-Mills theory, where it perhaps is a little less striking. In Yang-Mills theory, I have a 3-point interaction of this form, and then a 4-point contact term. And it's a pretty standard exercise to show that if you start out with just the 3-particle amplitude, and you compute, so the 3-point vertex, and you compute your usual contributions from that to the amplitude, so just the sum of those 3 pole diagrams, then on shell, it will give the right answer. You can always choose a gauge such that this contribution is exactly 0. We can always choose your polarization vector such that this vanishes. So this can give you the right answer, but if you want to check the water density, that K added into your amplitude with one leg taken off shell, take the polarization removed and then the momentum dotted in, you want that to be 0, then that only works when you include your 4-point vertex. And so you can retrospectively engineer, given that you have this guy, you can infer what this one is supposed to be from gauge invariance of the water densities. And the same is true here. And certainly Feynman already knew this, that if you take the 3-point vertex and you play the same trick, calculate the poles, you can actually retrospectively engineer what the 4-point vertex was supposed to be, and then you can repeat. Good. So of course the Feynman rules are messy for various reasons. One is that there's a gauge redundancy. Another aspect is that the amplitude is invariant under changing the field, so on the field redefinitions. So there are many, many different ways you can write your action, and the answer for these on-shell amplitudes necessarily have to be the same. Jim?
So is this the same thing as the old idea that we start out with the linear theory, and we calculate the energy in the perturbation, plug that back in, and calculate the next order, and so forth?
I think that probably is similar. It may be similar that generates nonlinear pieces. Actually, I think it's very similar to something Ted said yesterday in his talk, that he did a linearized calculation, but it somehow generated the full Einstein equation. I would think it would be more similar. It would be quite similar to that.
Feynman claimed that also.
I see. Good. Good. Okay. Very good. So Dan said, but why should this work? So let's talk about that. Let's keep our big function up there, and then let's do an example where we do scalar QED. So now what we have is just our usual action for QED. We have our field, and we could also have some 4-point term. And maybe what I want is to keep my signs the right way, and so on and so forth, the normalizations. So this term here generates two types of interactions. There's an interaction between the scalars and the photon, and then a 4-point interaction also. And this one, of course, gives me a 4-point interaction of my scalars, so my charge scalars. And now I'm just pretending here that I have massless charge scalars. If you don't like that, then think about this as high-energy scattering, where we can ignore the masses. Okay, so what should I expect here? Suppose I want to calculate an amplitude where I have two scalars interacting with two photons. So what will contribute on the Feynman diagram side are pole diagrams made out of the free vertices as well as the contact term. Set it up generically. But I know that this contact term is there only to ensure gauge invariance off shell. So I should certainly be expecting that I could recurse this from just knowing the 3-point information. And indeed, this is true. Recurse. This works. Now, if I do the same thing for my 4-point scalar amplitude, then for sure this contribution will be there. There'll be a lambda. And there's no way that a priori that the terms that come from here know anything about what the value of lambda is. So I should not expect to be able to recurse this amplitude. So this, of course, fails. Now, a small aside is that what do we actually get if you calculate it? So let's just recurse it with BCFW. And what you get is the following. You recurse based on the only 3 vertex in the theory. So you get something that's proportional to the coupling of the photon to the scalar. And then in this spin-helicity language, then you get something that looks like this. Okay. So you get an answer. It doesn't necessarily look too bad, but it disagrees with what you get if you do Feynman rules by a particular amount, and that is that the Feynman rules will give you minus lambda plus e squared 1 plus something, which is exactly that.
So is that because there's a pole at infinity?
Exactly. So thank you for asking all the leading questions. When I derive the recursion relations, I have to assume that the amplitude will go to 0 as c goes to infinity. In this case here, if I take the actual true answer from Feynman rules to the amplitude, there's a pole at infinity, which is equal to lambda minus e squared. Or minus lambda plus e, I suppose. Let's keep it straight. So there is one case in which I actually could recurse this, and that's when that pole vanishes. That means that my quartic coupling is determined by the gauge coupling. And when is that true? In supersymmetry. So lambda equals e squared. Susie. And indeed, if I did these recursion relations for n equals 2 supersymmetry, this would precisely work. Generically, though, in n equals 4, the recursion relations that are described here always work, with one small exception. There is one scalar amplitude it cannot detect because that scalar amplitude is 1. It's simply just the only contribution to it is the quartic. So the only way you can then generate that, and the natural way of actually doing recursion relations in n equals 4, is to teach your recursion relations supersymmetry. And so that is done by promoting the amplitudes to superamplitudes by including some Grassmann variables. And now you incorporate into your shift a shift of those Grassmann variables, which exactly is such that supersymmetry is preserved. And now your recursion relation know not just about gauge invariance, which is what really makes all this work, they also know about supersymmetry. So everything can now be determined from just a 3-point vertex. And in that case, if I do supergravity, if I know this vertex, I will know everything up tree level in the amplitude. Yes?
Okay, so I suppose that I took r plus, say, r to the third.
Good. Okay. So higher derivative terms. So for example, if we took r cubed. So generically, including higher derivative terms, we're going to run into problems because we need this condition that the amplitude goes to 0 when I take z large. Now, how is that normally arranged? If we think about a diagram, then the suppression at large z will come if I shift legs that go across here. The suppression for large z would have to necessarily come from the propagator. But if I have derivative interactions at the vertices, these ones can also depend on p. And for our usual gravity theory, they just depend on p squared. So already now it seems like a miracle that you can suppress anything at infinity. There's a little bit of a story also, which the polarizations help you with suppression too, as it turns out, by killing some of the terms. But if I have r cubed, of course now I have 6 derivative terms and things tend to go bad.
Suppose I make it r to the 4th.
Or r to the 4, yes. I mean, just so the story is general. R squared, r cubed, r to the 4th.
Then by knowing the 3.1, you can't recurse the
4.1. Exactly. So there is a general... Good, so let me comment on that just in a second. So the general story is the more derivatives you have, the harder it gets. But it turns out that at least actually for r cubed, this generates a 3-point interaction. If I take that 3-point interaction as my input, I can write down a recursion relation that will generate the 4-point amplitude I get from that vertex, which is my higher dimension operator r cubed with a regular gravity free vertex, the next order. This can actually be generated recursively. Okay, so this one I can certainly do in some cases, but those tend to be special. And then you made the other comment, which was, but even if I could do something with input from this guy, I can't know about r to the 4th and other things. And that's absolutely true. So we wrote a little paper once where we talked about when does recursion even possibly work. And you can analyze very generically and see when there are the possibilities of other independently gauge invariant terms that could contribute, recursion necessarily fails. And you can follow through and precisely match when it fails and when it works for some very generic cases. So the intuition is absolutely clear. You have to put in some knowledge of what is in your theory, what the gauge-independent quantities are, before you even have a chance of recursing them. And there was a very recent paper also from the Caltech gang with more general versions of recursion relations where you can improve on when they can actually work.
So when it should work, when you have all the gauge variant terms under control,
yes.
Is it easy to show this condition that the residue at infinity vanishes?
So actually, people used recursion relations for a number of years before it was more systematically worked out when this works in Yang-Mills theory and in gravity. And that was a paper by Cliff Chung and Nima in 2007, where they used the background field method to make this argument, and then follow up later by Cliff Chung that whenever you have, say, gluons or gravitons, then when the only things that couple to those things quadratically, then it also works. There'll always be a good shift in that case. Or that's a class of shift that always works. Yeah. Okay. Good. So this was the broad introduction part. What I'm going to switch to now is to mention a number of subjects that people have been working on in Yang-Mills theory or gravity, and then try to make some comments and context. So this is more as an overview of what is going on in some of the things that are going on in the field. So one thing we already touched upon was that gravity at the amplitude, onshore amplitude level, looks like gauge theory squared. And we saw that already from KLT, from strings. And our example was simply one that looks like this, and I said that it gets a little bit more complicated for higher point. And okay, and this was even maybe a little different from the other one. Now there is a way of, and this was tree level. There is a way of doing more interesting things with this relation that also tend to extend to higher point. So to see this, well, this is known as various versions of BCJ duality, BCJ doubling trick, and this is Baron, and it's Carrasco, who is right there, and Johansson. So they have another way of doing this, which is quite interesting, and to see this, let's start in gauge theory. So in gauge theory, I can always write my amplitude, here let's think of an endpoint amplitude, as a sum over diagrams where I insist on only counting cubic diagrams. And so let's think about diagrams of this form here. So dot, dot, dot. So this is trivalent diagrams. And what they will have is I can always think of writing them as some product of scalar propagators, whatever goes into that trivalent diagram, and then some numerator factors. And each of these numerator factors also come dressed with a color factor. So why is this allowed? What happens, for example, to the 4-point vertex? Well, a 4-point vertex is just a constant. I can always call that, say, S over S if I want to, and then S goes in over here, and there'll be some suitable comma factor that comes along with it. But of course, this is not unique. The point is just I can always write my amplitude as a sum over trivalent graphs, even just from the level of Feynman diagrams. Now these CI here's, let's do a simple example. I take an S channel, and my CI for this guy, let's see, for the S channel, would be a product of what comes in gauge theory of the structure constants from each of the vertex rules. So let's call this A, B, C, C, D, E, and with a sum here over those. And then, of course, if I do the same thing for my S and T channel, then for my S, T, and U channels, then I know that these ones have to sum to 0 when I pick my sign suitably by the Jacobi identity. So for each little subpart of my diagram, I can look at what happens when I replace, say, an S channel with its T and its U channel. Eventually, I'm summing over all possible diagrams. Some of those kinematic factors that sit in front could be 0, but that doesn't matter. I would always have subsectors of my big sum of diagrams that will look like S, T, and U channels. And those color factors associated with that will follow this rule. So the claim of B, C, and J is that I can always write my amplitude. Well, it's trivial that it can be written in such a form here, but the claim is that you can always pick pick the kinematic factors ni, such that the ni's that sit with the color factors that satisfy such a rule, which satisfy the same rule too. Can also pick the n's such that such that ni plus nj plus nk is 0 whenever the associated color factors do exactly the same thing. So this is a color kinematics duality, that the kinematic objects satisfy the same as the color ones. And you can certainly prove that this is always true and possible at tree level, that it works. That you can indeed pick it this way. Okay. So far so good. Now what does this have to do with gravity? Well, if this is the gauge amplitude, then their statement is that if I just take my expression here from my gauge theory amplitude with the n satisfying these Jacobi-like rules, and I replace my color factors with another n, then that calculates the gravity amplitude.
Same elicity, external elicity.
Yes. Yes, because that necessarily doubles. That's correct. But it's not. It also works in higher dimensions. It's not specifically four-dimensionally dependent. So Karas, sorry. Yes.
Yeah. Well, I'm just to get different states in the gravity theory, you'll take different helicities, so you'll double copy plus helicity,
exactly.
plus helicity.
Yes.
Well,
yes. Yeah. So good. So yeah. Let me answer that in a second, because
scalars is dilaton axion.
Oh, I see.
Yeah.
So now I'm just doubling, writing the same thing as before. Doubling, still adding, summing just over trivalent graphs. And that's supposed now to be my gravity amplitude. But it's even stronger than that, because they say that I can take two different copies. I can take two different representations of this, and just as long as one of them satisfies these relations, these Jacobi-like relations, then this will compute the correct gravity amplitude. So this really specifically gave a realization of gravity as gauge theory squared. I know my gauge theory amplitude, I directly get my gravity amplitude. And moreover, they argue that, this can be proven recursively using the recursion relations from this statement, which was put to at tree level, but it also is proposed to generalize to loop at the level of the integrands. Then you still have to worry about integrating those things, but it should. Yeah. Yes, Jim.
So does gravity equals gauge theory squared have some physical application beyond simplifying?
So I'm very happy you asked about this, because we should definitely have a talk about this. Where's Donald? He's there. So we will also come to that question of what happens, for example, for classical solutions.
Oh, right. We're in the next level, so it must be fast.
Did you say what the gauge group is?
SUN. For what everything I'm doing here, color doesn't actually matter all that much. So let's just think about SUN.
Where n is.
Color. Yes, good. Yeah.
Where n is.
Where n is whatever you want it to be. N is bigger than 1. N is bigger than 1. Okay. Now once you get to loops, I probably want to be in the planar limit. No, actually I don't want to be in the planar limit. No, I don't want to be in the planar limit. Still good for loops. Never mind that. Good. Okay. So good. So this is incredibly powerful. You can use this 3-loop level. It has been used at 3-loop level, 4-loop level, to calculate n equals 8 supergravity amplitudes at 4 point, directly from knowing input in gauge theory. And I guess 5 is not so happy, but so that we're not going to talk about that. Anyway, this double copy trick is very interesting. There's another interesting aspect of it, is that we know that for color factors, the Jacobi identity follows because there's a Lie algebra structure. So there's a question of, is there some underlying structure that gives us these kind of color identities too? then my next point was exactly to carry over to Jim's question. Then, if this is true for the on-shell amplitudes, what else do we know that it might be true for? So, next point is, what about classical solutions? So we talked about the tree amplitudes. The tree amplitudes are supposed to encode the classical physics, so somehow they should also encode what we can learn from the equations of motion. And you can take gravity, you can take amplitudes, and from amplitudes start perturbatively reconstructing the Schwarzschild metric. But it's not. I'm not sure I would say it's fun. The leading order is easy, and then you have to work very carefully in effective field theory reconstructing the terms. But now you could ask the question, which may be exactly what Jim was, that given that there is such a doubling trick that takes us from a gauge theory amplitude to a gravity amplitude, is there also a doubling trick that takes you from classical solutions, doubling from classical solutions in Yang-Mills theory to those in gravity? And Donald has worked on that. So maybe all I should say is that is an advertisement for his talk. When is his talk?
Next week.
Next week. His talk next week. And so anyway, this has some interesting aspect. One of the...
It works.
The what?
You wanted to know the answer? It works.
Okay. So one of the themes that seem to come up a lot is emergent space-time. And I don't know if you want to talk about that in this context too. It is kind of curious that you start calculating in flat space, and then curved space solution can emerge from those properties. Do you want to add anything, Donald?
No, we'll talk about it next week.
What is the gauge theory solution in the Gibbs version?
It's a Coulomb point charge.
Yeah.
You can match it exactly.
And in what sense is it doubled?
Well, it's in this BCJ sense. So the recipe, there are certain numerators essentially, there are propagators, and the squaring relation maps at the level of numerators once you preserve the propagators. So you can see this to all orders. In fact, it's essentially trivial.
Does the black hole have an interior?
Is it a formula that says G mu nu equal to...
This is classical. Maybe we can go further next week.
Yeah, obviously people would like to come to his talk.
All right, so now people will come to your talk. Good. So let's move ahead and talk a little bit about loops. And one thing you have to deal with when it comes to loop is the UV structure, that there can be UV divergences. And since we're talking about gravity, I just wanted to make a few remarks that one of the things that has been discussed in the field, and is perhaps still discussed in the field, is if the maximal supergravity theory in 4D could be finite. And one thing that for sure we know is that strictly below 7 loops, there cannot be any divergences, and this is a consequence of studying what the implications are of supersymmetry and E77 spontaneously broken symmetry. Yes.
Only in 4-point amplitudes or for arbitrary?
This statement I made here is true for any number of amplitudes. Yeah. So there's a very nice story there, which also connects to soft theorems, because this symmetry is not fully realized in the theory. It's spontaneously broken. So the way you impose that on the amplitude is through soft theorems. And if you take the BMS story for gravitons and probably fully supersymmetrize it to n equals 8, I think what happens is that the 70 scalars of the n equals 8 theory, their soft theorems must follow from BMS in some fashion. Okay. But anyway, yeah, they're just simply Goldstone bosons, even in the usual sense. Okay, beyond that, then since you asked Tom, add 7 loops, 4 points. If 4 point is finite, then you can prove that all point is finite. But for L greater than 8, even if you prove that the 4 point is finite, you have to worry about 5 point and 6 point and so on individually. There are infinitely many counter terms that are compatible with everything we know at this stage.
Is it the 7 or greater than 8?
Sorry, what was that?
You say greater than 8, greater than 7.
In greater than or equal to 8. Yes, correct.
Doesn't power counting limit the number of counter terms?
So the power count. So the power counting doesn't help. Power counting helps in Yang-Mills theory, but not in gravity because everything is two derivative coupled. So even when I add more
number of loops, let's say 8 loops.
Yes.
There is a finite number.
No, there are infinitely many. And for a given n-point amplitude, there are finite many. But even if I can compute up to 17 point that the amplitudes are finite, I have to worry about new counter terms that could appear higher point.
The higher point one will be r to the 17 or something like this, which.
I can also multiply by scalars. I can have some function of the scalars sit in front.
Okay.
And so on. So I can have arbitrarily many. Yeah. So there is no control of this as we know. It may be, and I think, it is possible, but I don't know how to state it precisely. I guess nobody knows at this side really, except in special cases, that these type of dualities can help restrict the structure of this order. There are some examples at low number of loops, but in general, we just don't know. Yeah.
Is there any connection with the asymptotic safety program, where
not that I know of.
Closes
no.
after 6 counter terms or something like that?
No, not any signs of that. Okay, so we talked about, or I give you a. So at UV, there's also a lot more going on. There's structure, lower supersymmetries, there are other dimensions. There's what is the critical dimension at a given loop order, and so on and so forth. So there's some interesting work going on there comparing with what people do in other aspects of that. Yeah. Yes.
If you do loops just for pure Einstein gravity,
yes.
Do you see the divergence of the cosmological constant come up in this formulation?
Oh, good. So in this story, we're strictly so anything that I would say about finiteness would be for pure supergravity, no gauging whatsoever, no cosmological constant. So pure gravity is finite at one loop, but if I include generic matter or cosmological, even with a cosmological constant, I'm not even sure what I'm expanding about. I have to expand around flat space. So if I include generic matter, then it's divergent at one loop. Yeah. So.
And you see the cosmological constant divergence, and then you just can't go on from that.
What do you mean? What I have to expand around flat space. So how am I supposed to do this?
Well, there will be some term that comes from has to be canceled by adding a cosmological constant around flat space and expanding it out as 1 plus h. Wouldn't you expect that from the way it works in field theory?
I would not expect a cosmological constant term because that comes in at the same order dimensionally. I would have, the one loop divergence would be encoded in an r squared times term bidimensional counting, and that's not the right dimension for a cosmological constant term. I would also say
dimensional regularization where she's only considering logarithmic divergence and not power divergence.
Exactly. Yeah.
Power divergence.
It's power divergence. Exactly. Yeah. So it simply follow the number. If I go up in loop, I go up in number of derivatives I have to put in. So one, yes. Okay. So then there's loops on IR. So generally, if we talk about gauge amplitudes, then we can talk about 2 types of divergences generally for the amplitudes. There are soft factors. There's a case where I take an external leg and it goes soft, which was exactly what we heard about this morning. And we have the Weinberg-Soft theorems and so on. There are very specific formulas for what exactly the soft factor get. And you get a soft factor times the remainder of the amplitude. Another thing that can happen is that you have two legs going collinear. And then there's another specific set of split functions that you go in front of it. There are two types of versions. So you have soft and collinear. And when I deal with loops, so suppose I have some amplitude here. Here is part of my internal loop. Here are some external legs. Then I also have to worry about when I integrate over the loop momentum that they can be soft. And if I do dimensional regularization, I get 1 over epsilon from that. But I could also have an issue when it goes collinear. And that can give me another 1 over epsilon. And so typically in gauge theory, I get at L loop order, I will have IR divergences that go as epsilon to the 2L. In gravity, we have soft, but not collinear. So we typically are 1 power down, so we just have 1 over epsilon at each loop order. Good. Now, good. So this was gauge. If I have gravity, it's 1 over epsilon to the L. So they're a little different. Now on n equals 4 super Yang-Mills, planar, one has very good control over the IR structure of the amplitude, and it has been shown that there's a resummation. And that resummation is basically an exponentiation and the names that go with that is AB, DK, and BDS. So Anastasio, Barron-Dixon, Kossover, and Barron-Dixon, Smirnov. And this exponentiation determines the IR structure completely. But it doesn't necessarily determine the full finite part. So there is a remainder function that was first noticed, I think, in Juan's paper with Fernando Alde from a completely different point of view, where you used ADS CFT to calculate amplitudes in the planar limit via a Wilson loop with the null polygon Wilson loops. So the remainder is basically the actual answer, if you wish, for the amplitude. So sorry, I don't know how to write this. Maybe just the actual amplitude minus what the exponentiation formula would give. So minus BDS answer. BDS. Yes. So this isn't necessarily IR finite because the explanation formula captures this part, but it's a structure that depends essentially just on dual conformal. Well, so I didn't say what dual conformal is, but it depends on certain cross ratios only, and that's an interesting function. So this function at the two loop 6 point, where this. What is it? Did I say it wrong? Oh, it's divided by. Sorry. Divided by. At 2 loop 6 point, then there was a heroic calculation that returned this answer as a 17-page result, and that was the one that Anastasia Volovich and Mark Spratlin and Goncharov and collaborators reduced to simply just a very much more compact answer. Good. Okay, so anyway, that was just a small comment to make contact with that. For gravity, as far as I know, we don't know any such control of the IR structure. Does anybody know if we know any control of the IR structure?
There's only one loop. You
at one
loop.
The one loop, yeah, but there's no resummation or anything.
No, there is the same resummation, but the answer
the
is.
usual resummation is not the Weinberg paper, the sums of.
The Weinberg, yes, okay, good.
The Weinberg.
Good. So the good. Yes. So good. You're right. Yes, good, very good. Okay, so yes, so we do have control over the IR. Yeah, I'm sorry. Yeah. Okay. All right. So that was the IR.
I'm a little confused about the difference between the gauge, the maximum infrared divergence in the gauge, and the maximum infrared divergence in gravity, and in particular, its relation to the gravity equals gauge squared world. How come that doesn't seem like that is consistent?
Yes. So that doesn't look. That's true. Good. So for this level here, when we're just plugging in at tree level, there's no issue, of course, because there's no IR divergence. Now, when I plug in, so I think a similar thing happens in QED, and it has to do with the fact when you sum over all possible insertions, you get rid of the aspect that has to do with the collinear divergences.
Not in QED.
Not in QED.
Gravity equals to,
Yes.
I mean, you don't take the square of the integrated amplitudes, right? You take the
That's
square.
correct. Yes. You have to square first and then integrate.
And in particular, the denominator appears only once. So
That's correct. Yeah.
Well, it has to do with the helicity too of the gravitons. Now I don't know how you see it in this language. The fact that to emit a graviton in a collinear direction, it's harder than to emit a photon in a collinear direction. You get an extra suppression, angular suppression.
Good.
And so in 4 dimensions, you're right, and there is no. Weinberg himself points out that you can go to the massless limit and there is no.
Good.
But I think
Yes.
this situation is more complicated than Weinberg thought it was in '65, and there have been some recent papers here. Somebody, and only very recently, when you actually start to do calculations, you see infrared divergences in gravity, and what are you supposed to do with them? And they
Infrared. There is no question that there are infrared. I'm saying collinear.
Yeah.
There are no collinear.
Yeah. That's correct. Yeah. Okay, so staying at loops, I wanted to mention loop recursion. So this is in super Yang-Mills theory, and again, this is you can play around with the integrated amplitude, but and that was done very early, but it was not easy. Now, what you can do is to do loop recursion for the integrand. And so you need a good definition of what your integrand is. And now, before we had a separation into just factorization into 2 parts, 2 tree amplitudes of lower point. You get similar stories for so the point is the integrand is also a rational function. So we can again play around, and for generic momenta, it will have just simple poles. But it has different types of simple poles than just a tree amplitude. It has the same type of poles where you can factorize into, say, something that is like a tree and something that is a bit like a loop. So that's the typical thing that you would have before. But you can also have other contributions that basically come from forward limits of the amplitudes. So the simplest example would be that my 4.1 loop amplitude, if I try to factorize it with recursion relation, and sorry, by this I mean integrand also, if I try to factorize it this way, I would end up with a 3.1 loop, and that the 3 point doesn't have a 1 loop correction, so that doesn't exist. So I only end up with a 4-point limit, and the way that works is that I take a 6.3, 1, 2, 3, 4, and then I join up in a forward limit to the legs. So this sounds extremely easy when you say the words. It's kind of visible how you get a loop out of it. But then when you actually do the calculation, I found it very hard. But we have done it, at least as an example, for 4 point to see how it really works in all the details.
This is planar.
Planar, absolutely. Absolutely planar. And in order for the forward limit to be well defined, you also need the supersymmetry. So this is a nice story. You need the planar part. You seem so I would leave it as a question whether anything can be done like this outside in gravity or otherwise. I mean, so of course with a super in front. But the planar might be a difficult part to get around. Okay. Geometrization. So in yesterday's question round, Yaroslav said he would like to see if there's a geometrization of the amplitudes in gravity, because it seemed to be so nice in n equals 4 super-Yang-Mills. So in planar n equals 4 super-Yang-Mills, we have a very nice story about describing amplitudes as contour integrals in a Grassmannian space. And there are actually 3 different formulations of that, but they're all equivalent. But one of them is particularly easier to work with. So the Grassmannians. Closely associated with that are the things that are called Onshore Diagrams. And the nice thing is that the Onshore Diagrams at least don't seem to rely so heavily on planar and the maximal supersymmetry. So in principle, you could define those in other contexts, n equals 1, pure Yang-Mills, and perhaps you could even do something on the gravity side also. And so there's a big question here of whether gravity has something to learn from these approaches. And of course, there's another word that I should put here, which is the amplituhedron. So one thing, what I mean by geometrization, is that through this description of Grassmannians, onshore diagrams, there is a picture in the lowest order where the amplitudes becomes volumes of certain polytopes in high dimensional abstract space. And this can then be generalized into the amplituhedron as some geometric form of what an amplitude is. And how and when and why, if it does generalize, we really don't know very much about at this stage. Maybe Yaroslav. Well, Yaroslav should give a talk. Or 2. All right, how are we doing? So, only just a few comments left. One is about symmetries. So again, n equals 4 super-Yang-Mills is a very nice theory to work with because it has these extra symmetries. It has the superconformal symmetry. But in the planar limit, it also has another copy of that. And together, they build a Yangian, so you have an infinite dimensional symmetry in your structure. And this seems to be very powerful. It's perhaps not completely clear how much of this is strictly needed for all of that. But in gravity, Andy has taught us that there is something that you can do with BMS, which I didn't know until his work, that there was things you could do with it. So this is really nice. I mean, and so it would be extremely nice to see how that would have an interplay, that you can actually use all this structure that seems to be there to learn more about the amplitudes in gravity and supergravity.
But there's also, I mean, there's also an infinite dimensional symmetry in the Yang-Mills theory itself.
What is the BMS?
Angle-dependent gauge.
Good, good. So you mean from BMS, or independently?
Just from gauge, from the gauge.
Just from the gauge. What? So somebody said, okay. All right. There is one thing in this context to say, which is the soft scalar limits. So there are the soft graviton limits we heard about. The soft scalar limits in n equals 4 super-Yang-Mills theory play a very nice role also. So when you take the scalars soft, you're at most of the stuff that's done here is at the origin of moduli space. But when you look at the soft scalars, they probe the moduli space nearby. But of course, the moduli space in this case here is not flat. You go on the Coulomb branch. And so you can actually show that when you take the scalars soft Here, you're producing the small mass limit of the amplitudes with masses on the Coulomb branch. And you can even, if you take multiple soft limits, you can show explicitly how adding up those multiple soft limits taken off the origin of moduli space resums the massive propagators of the amplitudes out on the Coulomb branch. So that's something we worked out some years ago, actually, with Nathaniel back there. So that's a nice connection. Maybe something more can be learned from that. Okay, I can mention just two other things very quickly, and then I'll end. One is that what about non-perturbative? And I think the only thing I have to say about that is that there's the work by Pedro Vieira, who describes amplitudes in terms of the Wilson loops with null polygon Wilson loops, and that's the only approach, it seems, that really go into the non-perturbative side of the story. And then there are another set of things, which are the so-called scattering equations, written down by Cachaso and collaborators. And that's a case that really seems to nicely unify between the Yang-Mills side and the gravity side and works nicely for both. So it's a different way of encoding amplitudes. The Grassmannian gives a completely orthogonal thing to the Lagrangian. The scattering equation gives a very, very different picture too, more string-like in some sense. So anyway, so I wanted to just list a bunch of different subjects that people are working on. And we'll hear more about that next week, I guess. Thank you.
Questions? Richard? I'd like to ask about the interplay between the infrared and the ultraviolet as far as loops go.
Yes.
So suppose you're calculating a loop diagram. As I understand it, they use this on-shell factorization and then basically bootstrap to go higher order. So they need the lower order things, and they need the finite parts of the lower order things too, which are all infrared divergent. How do they deal with that? When they make a statement that they've shown that something is ultraviolet finite at four-loop order, what does that mean specifically?
Good. So let me try to answer at one loop. So for one loop, I can do an integral basis of my amplitudes, which consist of boxes and triangles, bubbles, and so on, and then possible rational terms. And if I'm in the maximally supersymmetric case, then only this guy appears. So in that case, and I should say that everything that could possibly be IR or UV divergent sits in the bubble. Everything else will be nice and finite. So in that case, when these are absent, I know exactly what's going on. At higher loops, we don't have a complete set of bases and so on, so it may be a little bit harder to answer. But at least in this case, you know exactly what's going on.
They claim to have done four-loop diagrams, and they're working on five-loop.
Yes.
How do they deal with that? What does it mean when they say that they're at four-loop order? How did they deal with the infrared problem in the finite part at 3 and 2? And
we should let John Joseph answer.
You introduce a separate IR regulator, different from dimension regulator. That's one version. Introduce a separate IR regulator and then just focus on the UV. And just do the UV part in dimension regularization.
I see, and there's never any coupling between the finite part of the infrared stuff and UV?
In fact, observing that there is no coupling is in fact a sign of consistency of the approach, and the fact that the IR regulator is in fact a consistent one and does not.
What IR regulator do you?
Anything else. Excuse me?
What IR regulator do you?
For example, a mass, a uniform mass.
For gravity?
It works just because there are no divergences at lower orders. There's of course something bad that happens if one were to look at the next order in the expansion around UV to leading orders. Alternatively, if you don't like a mass, we can just not integrate all the way to zero.
With the supersymmetry.
Yeah. Alternatively, we can just not integrate all the way to zero moment. It's just as fine. Okay.
Can you say where the twistor string fits into this?
Here. So good. In the context of n equals 4, yes. So the twistor string fits in at this stage here. I mean, I'm not sure how much I should say. I mean, there's certain ways of getting between this formalism and some of the other formalisms for the n equals 4 maximal supersymmetric case, and related basically also to the Grossmanian story. Yeah.
Let's say I want to apply this kind of formalism in a different background and to make it simple for you, maximally symmetric. Let's say this is how do I proceed? I mean,
that was not making it simple for me.
Okay.
So
I give the background. I mean,
but
I mean,
if you want,
is there anything I can apply from this kind of formalism?
So there's been some connections between this formalism and correlation functions in ADS, but I don't know of any. I don't think I know of any scattering in general backgrounds. How to appropriately set it up and make as much mileage out of this.
Anything else?
How much of this simplification that occurs is due to going on shell, and how much could be achieved by working in specific gauges with specific choices of field variables?
Very, very good. So you can, for example, in Yang-Mills theory, there's a way of encoding one set of recursion relations at the level. You can encode some of this at the level of the action. So you can do this at the cost, for example, of getting a non-local action. That's one way of going about it. That's giving you the so-called MHV vertex expansion. That's one way of doing it. The BCJ relations, there's a way of engineering.
So that would be a non-local choice of field variable or a non-local gauge or both?
It's you do a field redefinition that makes your action non-local. So you have 1 over box and so on in your action. For BCJ, there's a way of reintroducing terms in your Lagrangian that are really practically 0, but then play the role of giving you the form of the BCJ relations with the color kinematics duality explicitly. And you have to work order by order. How many points did you go to? 5, 6?
They went to, I mean, there's an algorithm to go to n points.
You can in principle, but yeah, explicitly it was 6 points. Yeah. And so it's a way of adding 0 to reaction in that case, but it doesn't. It's a principle of showing that it in principle can be done, but it's not necessarily a calculational efficient tool to work with.
Well, as Tomislav indicated, we have very heavy problems working in the sitter background where all we can do is correlate
yes.
terms, and it would be just wonderful if we could do some of these simplifications.
Right.
I'd love to see what it is.
There is.
Yeah, so Raju, he derives some recursion relations for gravity amplitudes in the zeta rate for ADS. So you can do something similar to what.
This is pure gravity?
Pure gravity, yeah.
Right.
Okay.
Okay.
Thank you.
Thank you.